Thank you very much for that introduction, and also to you, Matthias, and Helmut Veit and Thomas Eiter of the Program Committee for honoring me with this invitation. It is a great privilege to speak at this meeting. So let's start, as suggested we should by Professor Scott in his opening remarks, with the history. And for me, this goes back to Tarski's work in the 30s, 40s, and 50s. This is an old-fashioned Blackboard talk, by the way, so by all means move forward if it's not visible. I think it's okay at the back, though. Okay, so the work of Tarski in the 30s, 40s, and 50s, he set himself the task, well, many tasks, but the one I'm focusing on is the one of discovering what the definable sets in real Euclidean space are under the signature of the algebraic operations of addition and multiplication. So throughout this talk, well, unless otherwise stated, I'll only be looking at structures with domain the set of real numbers, and for the moment, the signature, or the language, I'll be considering this as a structure in, we'll just have symbols for ordinary addition, multiplication, the ordering, and the constants 0 and 1, although sometimes I'll be using other parameters, real numbers as parameters. And we're interested just in first-order logical definability in that signature. So, so the question, is that visible down there? Can you read it down here? Yes? Yeah. Okay. Which subsets S of n space are definable? Well, let's first order definable. So by this I mean, for which subsets S is there a formula of this language in n free variables that picks out in this domain precisely the elements of S, the n tuples that lie in S. And it's a very famous theorem. So this is all due to Tarski, is that, let's say it like this, such S can, in fact, be defined by a formula with no occurrences of quantifiers. In other words, given any formula phi in n free variables, we can find a formula psi in the same free variables, which is equivalent to that formula in this structure, and has the property that it contains no occurrences of either the existential or universal quantifier. In other words, it can be represented in the form, well, just by using usual Boolean, conjunctive normal form here. It can be defined by a formula of this form, where the Pij are polynomials with just integer coefficients, And this symbol is either greater than or equal to. You can have combinations of those, and just with the Boolean conjunction and disjunction applied to them. Now, if we allow other real numbers to occur as parameters in our formula, the same result is true, except you have to allow polynomials in those parameters to occur as coefficients here. Now, what I'm not going to talk about is the effectivity that there is in this result. That's a very big area. In other words, given a formula defining S, it is true you can effectively find these polynomials, and the actual complexity of that decision procedure is a very big issue indeed, and very widely studied. But that's not something I'll be talking about, although I will be talking about a slightly more abstruse complexity issue later on. Now, this has the consequence, I won't write it, but you might like to think about it as an exercise. These sets here, things described like this, are called semi-algebraic. And one consequence of Karski's theorem is, for example, if you take the topological closure in R to the n of a semi-algebraic set, then it too is semi-algebraic. And the reason for that is that you can clearly define the closure by using the usual epsilon method. For all epsilon greater than 0, there is a point here within epsilon of the given point. But that requires quantifiers, of course. And according to this theorem, you can eliminate the quantifiers and write the closure in this form. Now, you try and do that directly. It's really non-trivial, even for n equals 2. Or even n equals 1, actually. You have to think a little bit about doing that. I can assure you, you don't get the right answer simply by replacing strict inequality by weak inequality. That doesn't work. But so that's one consequence. Now, so the idea we'll be working with in this talk, what I'll be focusing on, is trying to extend such properties of semi-algebraic sets, that is closure under topological closure and various other geometrical operations, to other classes of naturally occurring functions. So actual functions that occur in, say, an undergraduate analysis course, or well, just naturally occurring functions, to try and study the definability theory of these other functions. Now, unfortunately, it is, well, I can't really say this is a theorem, but it's because I'm not going to state something precise. But I give you a challenge. If you look up any undergraduate textbook in analysis and hand me a function that's mentioned there, I will be able to construct you a formula using that function together with plus and times, which is not equivalent to any quantifier-free formula. So Tarski's theorem is pretty special to this language. It's morally true that no other functions will, or no other single function can you add and still get this elimination of quantifiers, as it's called. I'll make that a bit precise later. But to get round this, let me just mention a corollary of Tarski's theorem, which was observed by Tarski himself, although he didn't really do anything with it. He said, well, let's just look at the case n equals 1 here, where these are just polynomials in one variable. Well, then it's pretty clear that the truth value of this formula, just depends on x, will only change when you cross one of the zeros of one of these polynomials. And so that tells us that, so this is for n equals 1, if S, a subset of R, is definable, then it is a finite union of just open intervals and singleton sets. So I'll just call those points. Okay, because it's fairly clear that sets just of that form, where this is just one variable, are of that form, and this property is preserved by taking finite Boolean combinations. So, and Tarski made this observation and didn't actually do anything with it, but there's a brilliant, so we now go on to the next person in the subject, Van den Dries, so this is now in the 80s, who observed, just a heuristic, that most of the geometry and topology that had been studied of semi-algebraic sets, so-called semi-algebraic geometry, which is a very big subject in its own right, most of the at least qualitative theorems that had been proved there could actually be proved just from this property. And the quantifier elimination. So with Tarski and this property, that all definable sets in one variable of this form suffice to deduce most of the properties of semi-algebraic sets. So he turned it into a definition, and that's the definition of O minimality. So, okay, so now L is now any signature suitable for the real numbers. So we have these, and then we have some other relations in several variables and functions from reals to reals, and we're now going to study the definability in this expanded language. So, right, I'm going to have to use a squeegee mop. And he simply turned Tarski's observation here into a definition. So, okay, so let's call the structure, well, let's say L tilde is an L structure. So this is just, still has the operations of addition, multiplication, and the ordering, but we have interpretations of these extra relations and functions, and then that structure is called O minimal, I'll say why in a second, if every definable in this extended language now, perhaps I'll put a tilde there to distinguish it from the original one, every definable, L tilde definable subset just of the line is, etc., a finite union of open intervals and points. Or another way of saying this is that every definable subset of R is definable just with the ordering. Well, allowing some parameters. This is with parameters. That is crucial. So you allow yourself a constant for any real number in your definition. So in other words, every definable subset of R is definable just using the ordering. And this is, and the little o here is nothing fancy, it just stands for order. So it's order minimal. It's the minimum number of definable subsets of R that there possibly could be, given that you have an ordering. And then Van den Dries, in his excellent book, went on to develop calculus, geometry, analysis, just for definable sets and functions in a no-minimal structure. And had got some amazing results, especially when you consider that the definition only involves subsets of the line, but one already gets consequences for subsets of the plane, r squared, r cubed, and so on. It places huge restrictions on those, although even in the semi-algebraic case, those sets, of course, can be quite complicated. Okay, I'm actually going to do a proof, just to give you a flavor of how this axiom is used. And basically what it does is remove all the pathologies of that you sometimes get in analysis that can occur with continuous or even differentiable functions. All the pathologies like space-filling curves, continuous, nowhere differentiable functions, all those things disappear. So just a small flavor of this I'll give you, and you'll see how this axiom is used. Suppose, so R tilde from now on is a no-minimal structure. So just any expansion of the ring of real numbers by functions and relations satisfying this property. No reference here, note, to quantifier elimination or anything like that. This definition is for all definable sets, and in general, the structures we'll be seeing don't have elimination of quantifiers. Anyway, so R tilde is a no-minimal structure. So suppose f from R to R is a definable function. What do I mean by that? I simply mean that the relation f of x equals y can be given by a formula of this language. So its graph is a definable subset of R squared. Okay? So suppose that is a definable function, then the limit as x tends to infinity of f of x exists. Well, either as a real number or plus or minus infinity. So an immediate consequence of that, by the way, is that sine x could never be a definable function in any O-minimal structure. This limit as x tends to infinity certainly does not exist. And the proof, very briefly, well, I'm going to use a principle that's an immediate consequence of the definition there, namely what I sometimes call the principle of asymptotic determination. One consequence of the definition is that if S is a definable subset of R that contains arbitrary large real numbers, then it contains all sufficiently large real numbers. Right? Because if it contains arbitrary large real numbers, and it's a finite union of intervals, then one of these intervals has to be of the form A infinity. And so it contains all sufficiently large real numbers. So let me just call that AD. So asymptotic, how shall I say it? Asymptotic determination. And it's true for all definable subsets of the line. So, so the proof here is, well, if f of x does not tend, say, to minus infinity, then there exists a constant c such that f of x is greater than c for arbitrary large x. And therefore, for all large x, therefore, by asymptotic determination for all large x. Similarly, by considering plus infinity instead of minus infinity, fx is greater than some other constant symbol, constant for all large x. Otherwise, it would tend to plus infinity. Less than. Okay, now all we do is subdivide the interval c prime c. So now just say consider, wait a minute, what, fx, yeah. Now consider c, say c plus c prime over 2, and c plus c prime over 2, that's closed, I suppose, c prime. So now we have two half intervals. It must contain arbitrary large x in here or arbitrary large x in there. So one of them, it must lie in from some point onwards. Now just keep subdividing and you'll find the limit. Okay, so that's the, so just divide and conquer, as they say. So there's one property of O-minimal structures that follows immediately from the definition. And Van den Dries went on to prove many, many more, although let me just pause to say that there's something unsatisfactory about that proof, in that it does use, in an essential way, or apparently in an essential way, the Archimedean property of the reals. Yeah? You couldn't do that proof in an arbitrary, let's say, densely ordered set, which was not necessarily Archimedean ordered. And this gave rise, or this kind of consideration, gave rise to a couple of years after Van den Dries made the initial definitions to Anand Pillay and Charles Steinhorn developing O-minimality in a much more abstract framework by working with just arbitrary, well, let's say densely ordered sets, where you can still make the definition. So the proper definition of an O-minimal structure just occurs on a densely ordered set with possibly extra relations and functions, and you make the definition and they develop the theory in that context, and then everything becomes much more first order. You're never allowed to use the Archimedean property, for example, and you can still do arguments like this. They found ways around it, and the advantage of that, even if you're only interested in the real numbers, you have an advantage of getting all your results uniformly because you're doing them in, let's say, arbitrary models of a particular theory. So you're allowed to use the compactness theorem from first order logic, whereas you're not if you stick to the real numbers. So they really lay the foundations, and one consequence of their work, so other properties. So I'm going back to the reals now, but you do really need the abstract framework to be able to prove these properties even for just the reals. Namely, so I'm going to call this star because I'll come back to it. If S contained in R to the n is definable, so one needs to go through a whole battery of lemmas before you get to results like this. But starting with proofs like this, or their generalization to arbitrary sets, then S can be written as a disjoint union of sets Si, where each Si is actually homeomorphic to full n space for some n, so ni space, homeomorphic to R to the ni for some, possibly different ni's, so some ni. Well, in particular, it's connected. That's what I'll need for, it's topologically connected. Now, further, and this is crucial, and this Van den Dries didn't achieve. This was only achieved when Pillay and Steinhorn put the whole definition in a general framework. Further, n can be chosen, so the number of sets that you partition your original set into independently of any parameters. Okay, so we allow, throughout, I'm allowing constants for real numbers to occur in the definition, but almost always, when you get bounds like this, or theorems like this, your the number of nice sets you decompose your original set into that always has an upper bound that's independent of those parameters. It only depends on the actual formula that you're plugging the parameters into. Okay, let me just mention a few other things that you can soon develop using the O-minimal axiom. So I mentioned calculus. One can show every definable function is always differentiable apart from finitely many points. And since using plus and times, you can easily define the derivative of a definable function, and it is also differentiable, the derivative will be differentiable at all but finitely many points. So the original function is twice differentiable, and so on. And so, in fact, you end up with showing that every function is actually infinitely differentiable apart from countably many points. One cannot do better there, by the way. There are examples where you can't reduce countable to finite in that last statement. Okay, so that's all I'm going to say about the general theory for the moment. Of course, all this would be a bit pointless if there were no new examples other than the original theory of just the real field. But there are plenty of them, and they're arriving thick and fast all the time. And when I've given a few of these examples, I'm actually going to go back to the semi-algebraic situation and show you a result that's really just about semi-algebraic sets, but as far as one can see, cannot be proved by staying within the semi-algebraic framework. One has to go to a bigger O-minimal structure or a more expressive O-minimal structure in order to prove the results, as I'm going to state. So, so examples of O-minimal structures. Probably one of... I think I'll get rid of that now. Okay, so here's a famous one, Rn. So I guess the O-minimality of this goes back to 1969, and Gabrielov, or though later treatments by Denef and Van den Dries exist. Well, this is, for those that know, this structure has the property that all bounded subanalytic sets are definable in it. So, but if you don't know what that means, I won't give an explicit description, but just tell you that it has this property. Suppose f of x is a function that has a power series expansion, real power series. And suppose that converges and equals this on some positive radius of convergence, possibly infinity. The so-called analytic function. Then this structure here has the property that f restricted to the interval minus little r is definable. For r strictly less than big R. And that's crucial. I already mentioned the sine function. Of course, the sine function has such an expansion with big R equal infinity. But you can't define f on the whole, the sine on the whole real line in any O-minimal structure, as I've illustrated. So it's crucial that you restrict here to intervals strictly smaller than the full radius of convergence there. So, but that's a lot of functions still, right? So that would get us the trigonometric functions, for example, and the exponential function restricted to bounded intervals. So all those functions are definable in some O-minimal structure. Another example, so I'm only going to do two, and these tend to be the only two that are used in applications. The next one is R and exp, which is the same. So this is the O-minimality here is due to Van den Dries and Miller. And this is just everything that you have in Rn, whatever that is, but certainly all those functions, together with the full exponential function. So, so that's for x on all of the real numbers. Which you don't have here. You only have it restricted to bounded intervals here. But in fact, you can add it, and you still get an O-minimal structure. So let me do an immediate application of this to semi-algebraic sets. The fact that this is O-minimal, and I mentioned I was going to talk about a certain type of complexity. So I'm going to start with a theorem of, believe it or not, Descartes. I think that's perhaps looking at history a bit extreme, but this is something that was called Descartes' rule of signs, I think. And this says that if you take a polynomial p of x with real coefficients, and you're really not interested in what the exponents are, they're certain natural numbers, but you have a certain number n of additions involved. And those d's can be arbitrary large natural numbers. Then the theorem is that this has an upper bound to the number of real zeros independent of the d's, but only dependent on n. In fact, I think it's less than or equal to 2n plus 1 real zeros. Of course, it still has dn complex zeros, but real zeros independent of the degree. And there was some work on measuring the complexity of semi-algebraic sets by the number of pluses used to define them, ignoring the number of multiplications. And some progress was made here. And so let me just show you how O-minimality of this particular structure can extend this theorem to many variables. Now, of course, a polynomial in many variables will always have infinitely many, even real solutions in general. They'll split up into curves. But we do have the following result. So really, the question is not about the number of zeros, but the number of connected components of zeros. which of course is the same here. The number of connected components of zeros is the same as the number of zeros. So one can prove the following theorem, and I'll attribute this to Riesler, sort of thought of the idea of studying additive complexity of semi-algebraic sets. So let S be a subset of N, be semi-algebraic, so S is of the form so we have a n tuple of variables and symbols plus or equals 0, various combinations. Then S has less than or equal to some constant depending only on, well, the dimension n and d connected components, where d is just the number of pluses. Occurring in all the Pijs. So you just add up the number of pluses, ignoring the multiplications, and call that D, however many there are. Then the number of connected components here, the number of connected bits that this set breaks up into, sorry, of course I mean here the x in R to the n, such that that formula holds. So this will break up into a load of curves and lower dimensional surfaces and things. But the number that you can write this in the form, the union SI I had before, is bounded independently of the number of the degrees of these polynomials. It just depends on the number of pluses. And I can, the very quick proof that I'll just say is, well, first of all, one considers this set separately on the 2 to the n quadrants in R to the n. So let us suppose we just work in the positive quadrant, and then you just make a transformation of put minuses on the variables for the other quadrants to reduce to that case. So if you're in the positive quadrant, we just substitute a new variable and its exponential for the old variable. So very quickly, the proof is replace, in this positive case, xi, the ith variable, by e to the yi. Now, if you do that, then the exponents in these polynomials, so just think of a monomial here, become parameters. Which they weren't. They were part of the data if you just consider this as a semi-algebraic set, but they're not part of the data if you consider them as an exponential algebraic set, so to speak. So you see, if you have a monomial, so I better not put that there. So e.g., so something like x1 to the k1, x2 to the k2 becomes e to the k1 y1 plus k2 y2, right? When you make this substitution. And now you can regard these k's as real numbers. They are, in fact, natural numbers, but you think of them as real numbers, and they're just parameters in a fixed formula considered as part of this language. Because, oh, sorry, yes, okay. And so we can use, so now use star. That's disappeared a long time ago, but that was the representation of an arbitrary set as the sum of n connected sets where n is independent of the parameters. So n is independent of the k1 and k2 there. When you make this substitution for all the monomials occurring in these polynomials, you get and the only thing that makes this a long formula in this language is the number of pluses. The exponents just become part of the, become new variables. And so you can use the fact that it has n connected components where n is independent of these k1 and k2 to prove this theorem. Okay, so that's a small example where you have to use a sort of what one might call a transcendental method to prove a fact about just semi-algebraic sets. And you go to the O-minimality of this structure in order to go back to the algebraic sets. Right, let's see, where am I now? Yeah. Yeah, well, for that, you have to look carefully at the proof of that structure theorem in this particular structure. Actually, you don't need the and there. We never use any other analytic functions apart from this. You just and this structure is actually what we call model complete. Every formula is actually equivalent to an existential formula in this structure. But not a quantifier-free formula, an existential. And you have to look at the proof of that theorem. And so it's nasty. It's very nasty, I'm afraid. It's nothing like 2n plus 1, like the Dirichlet case. Well, one could go back to some work of Hovansky on which the model completeness result of this is based. And there are more explicit bounds. Actually, yes, I might stick my neck out here. I think at worst double exponential in D. Oh, in N. No, that might iterate the exponentials. I'd better be safe and say that. I'm not sure if it really does, but I think... yeah. Okay, thanks for the remark. And, right, okay, I've got, what, quarter of an hour, I think. And so we'll do some recent stuff. Oh, I've got to use the squeegee mob again. Okay. Okay, I'm now going on to some recent work by myself and Jonathan Peeler, which was beautifully summarized in Matthias Aschenbrenner's plenary talk at the Logic Colloquium yesterday, so apologies for those that were there. I won't do anything nearly as expansive as he did there, merely just describe the theorem, I guess. Okay, so some recent stuff. Right. Okay, I suppose the motivation for this is purely number theoretic. In fact, it's to do with transcendental number theory. And there's a sort of philosophy there that you find occurring in Lang's books from time to time, and other people implicitly have the motive at this kind of philosophy that if you have some kind of naturally occurring, let's say, hypersurface in n space, and suppose it contains what appears to be more than its fair share of rational points or integer points, then the philosophy says this must be due to some algebraic reason. There must be some, say, algebraic subsets of the original set that are causing this. Now, saying more than its fair share has to be defined. You certainly can't use infinite there. one can easily have transcendental curves with infinitely many integer points on that has nothing to do with the algebraic part of the curve. For instance, you just take the graph of the function 2 to the x, y equals 2 to the x. I mean, contains infinitely many integer points, and it's completely transcendental, that curve. There's nothing to do with anything algebraic. So more than its fair share certainly cannot mean infinite, but there's also the problem of what do we mean by naturally occurring. It's easy to create examples of even complex entire functions with the property that are transcendental and have the property that it and all its derivatives take rational values for rational arguments. This is very easy to do because you have such flexibility even for entire functions. So so naturally occurring has to be carefully defined, and well, I guess since we're working in no minimal structures, that's what we're going to take as the definition. So so this is a theorem. Oh dear, sorry. It's like we used to use lemon juice to write secret messages. You know, kind of okay, so this is from 2006. So the idea is that if we have a definable set in a no minimal structure that contains more than its fair share of rational points, then this is for an algebraic reason. So this is the theorem. So let S be definable. Okay, that always means in some O-minimal structure. As I say, most of the applications are when you take Rn exp as the O-minimal structure, but any O-minimal structure. Actually, it's perhaps a little relevant to this, that I was going to mention, but not write up, a few other examples of O-minimal structures. One very famous function that is not definable in Rn exp is Riemann's zeta function, well, restricted to real values, which is where it's not particularly interesting, but one's interested on the critical strip, of course, but it's periodic there, so, or almost periodic, so that's not definable. But say for positive real values, the Riemann zeta function is definable in a no minimal structure, but not in Rn exp, but it is. So it would be covered here. So let be definable in a no min, yeah, I'll just say definable. Assume that this is a very transcendental set, has nothing to do with anything algebraic. So assume that S contains no infinite semi-algebraic subset. Then the conclusion is there can't be many rational points on S. Now, y equals 2 to the x is an example of such an S, so not many cannot mean finite, and it can't even mean logarithmic in some sense. It has to be more than that, but okay, so the theorem is then for all epsilon greater than 0, there's a constant C epsilon such that for all h greater than 0, S contains at most C epsilon points Q1 up to Qn, which are rational, with the Qi's having numerator and denominator bounded by h. So numerator and denominator less than or equal to h. So we take a large number h, and we ask of all the, well, what are there? H to the 2n possible rationals with numerator, roughly, with numerator and denominator bounded by h, how many of those can actually lie on the set S? Well, the conclusion is either there's an algebraic subset of S, an infinite one, or if not, this is at most, this number's most h to the epsilon for every epsilon. Now that's not a great bound, really. One would kind of expect something like log h to a power, and there are certain situations where we've conjectured such a thing holds. However, in this degree of generality, I'm afraid it is the best possible. There are examples due to Bombieri and Pila of just an Rn definable subset of R squared with the property that, well, it's slightly difficult to say, but you can't replace the epsilon by any function that tends to 0. It has to be a fixed epsilon. Now, I wanted to do a quick application of this. Now, I want to do at least one. I'm not sure if I'm going to get through this. Let me just say one. Well, it's my favorite example of a problem. This problem, one of my favorite examples that I ask people, that has a 5-line proof, but it's pretty tough to find. It was a Putnam Prize exam, I think many years ago, over 30 years ago. And none of the students managed to solve this particular problem. The problem was you're given a real number alpha, positive real number, and you're told that n to the alpha is a natural number for all n in n. Okay? And what you have to prove is that that can only happen if alpha is a natural number. Okay, now that defeated all the Putnam Prize competitors that year. Now, you wouldn't have expected them to use this theorem, but of course it does follow immediately from this theorem because the function x to the alpha is definable in Rexp, right? With parameter for alpha, because it's just e to the alpha log x. So the exponential and therefore the logarithm are both definable functions. So that's a definable function, certainly. And so this says there are certainly at most h to the half, say, natural numbers less than h, such that, well, let's... no. If we take numbers less than h to the 1 over alpha, then there are certainly... this would say, we take epsilon 1 over 2 to the alpha, 1 over 2 alpha, I think, and you'll get a contradiction to this, because this says there are about h to the 1 over alpha points of height h, whereas this would say there's got to be fewer than that, because this is definable, unless the graph of this function contains an algebraic set. Well, the only way that can happen is if alpha is a natural number. Would have to be a polynomial. But, okay, obviously that wasn't how they were meant to do it, but yeah, so there's a little challenge. So at least I mentioned one application. I do have little time to mention the other. I wanted to mention the proof, but I won't have time to do that, or perhaps I can say a few words. But this, I wanted to mention this because this is where it's kind of all at the moment. So this is to do with a very difficult, even to state, conjecture called the André-Oort conjecture in number theory, which is again a conjecture making precise this philosophy about excessive rational points on a set must be due to an algebraic reason. In this case, it's more to do with points on a discrete subgroup of the complex numbers lying on algebraic varieties, and the conclusion you want there is that that can only happen if somehow the group equations are embedded in the definition of the variety. That's the only way it can contain lots of points from a discrete subgroup. And so I just mentioned it is a corollary of this theorem. And I have to mention there's a number theorist, Umberto Zanier, and this is called the Zanier strategy, which was described very nicely by Matthias Aschenbrenner yesterday. And I'm going to mention the very simplest case. In fact, this already occurs in a paper of Lang in the 60s, this particular instance, but it gives something of the flavor. So just for two variables, let Pxy be a polynomial with rational coefficients. And I have to say that it has to be, for this statement, absolutely irreducible. That means it has no factors, even with coefficients over the complex numbers. Not just over the rational numbers. Not just irreducible, but absolutely irreducible. And so the conclusion is that there can only, so number theorists, so the group under consideration in this particular theorem are the roots of unity in the complex numbers. That's the discrete group that's of relevance. The reason for that I can't really explain, but so the conclusion is that this only contains finitely many roots of unity x and y that make this zero, unless there's a group law embedded within the polynomial equation here. So, so let's put the conclusion like that. Then if P of Z1, Z2 equals 0 for infinitely many pairs Z1, Z2 in the group of units, the roots of unity, so I'll call that U. So this is just the set of complex numbers C, Z, such that Z, if I used n anywhere, no, let's say m, equals 1 for some m. So these points on the unit circle, the periodic points on the unit circle. So if that has infinitely many solutions in that set, then it sort of has to define a group itself. Then Pxy must be of the form. So it can happen, but it must be of the form x to the n. Oh no, let's use it. Let me do it a different r then. For some r in n, x to the n, y to the m plus or minus 1, or x to the n plus or minus y to the m. For some n m. And so if you put these equal to 0, it's rather obvious that they've got infinitely many solutions in this set. In fact, you can take any one for x, and you can always find another root of unity for y in both cases. But they're really defining, in some sense, this group. But if that's not the case, then there can actually only be finitely many solutions. So that's the simplest case of a huge program about points on algebraic groups and many other things on varieties that are now beginning to be solved using our theorem over here. And in fact, Pila has recently even solved some cases of the conjecture, which is a general form of this, conjecture general form of this, which previously were only known under the Riemann hypothesis. And he's managed to use the O minimality to eliminate the use of the Riemann hypothesis, as well as establishing other cases as well. So I'll finish there. Thank you very much. A lot of people. Yeah.
Please. Could you comment on elimination of quantifiers and non-minimality?
Okay. So I said that you never get quantifier elimination. So the exact theorem is this: if you have the a analytic function defined in the neighborhood of 0, and if when you add it to the usual language, plus and times, if you get quantifier elimination, then the f was already definable. It was algebraic. You never get quantifier elimination. Over, if you take all the analytic functions, as we do in Rn, and you add 1 over x to the language and say make that equal to 0 if x is 0, then you do get quantifier elimination in Rn. So so this is why I mentioned Van den Dries and de Neef after Gabrielov. Gabrielov proved the model completeness of Rn. He proved every formula is equivalent to an existential one. But then Van den Dries and de Neef prove that if you take the language of Rn, which is just you have to add all analytic functions in all numbers of variables, and you add a symbol for 1 over x, if x is non-zero and 0 otherwise, then that does have QE. But you see, that's a massive language. It's an uncountable language, so it's a bit difficult to talk about decidability questions, although of course, for any given function, you're only going to use countably many new functions to eliminate the quantifiers. But as for effectivity, I know, did you ask about effectivity? That's a very different issue, because there's always problems with just applying transcendental functions just to 0, knowing whether that's 0 or not. I mean, those are very difficult questions, computably difficult.
So I have a question of my own.
Oh, yeah.
That you take for the O minimality the line
in the definition. Yeah.
Yes. Is it really important? What happens if you go up?
Well, okay. Well, already for the line, this implies these many structure theorems for sets in higher dimension. I mean, it just implies
of course,
them.
Yeah.
But suppose you took the definition for the plane, so if you said every definable set is a union of rectangles or something like that, well, I imagine that would, I can't see that anything could then be, well, I don't know. Anyone know? I've never ever seen anyone even attempt that, actually. Well, it's false in the semi-algebraic case, of course. I mean, so you'd only, and it's even false just with addition, I think. Well, okay, I mean, one can formulate a general definition of minimality where you'd given any two languages, L1 a sub-language of L2, and say it's minimal if every L2 definable subset of the domain is actually L1 definable, and then see what happens. And that's been done in several cases. But then actually to postulate an axiom on subsets of the plane, I have never seen, to be honest. I imagine it would trivialize almost everything, but no, I don't know that. No.
I have another question. O minimality is giving you a form of cell decomposition, essentially.
Sorry?
O minimality is giving you a form of cell decomposition, essentially.
Yes,
right?
Which I didn't mention.
Topology-wise, you can view as a generalization of the simplicity of linear algebra, because you just get finitely many cells.
Yeah.
Now, how far does this analogy go? What can you say of the simplicity of linear algebra in O-minimal structures?
Right. Now, of course, most O-minimal structures come from considerations of the functions that naturally occur in analysis. Now, in order to... I don't know what the consequences in algebra are, but you certainly have to know lots of algebraic facts about, say, germs of analytic functions in order to prove the O-minimality. For example, if you take all germs of analytic functions about the origin, this is an Noetherian ring. And there's lots of, well, commutative algebra anyway, that goes on in the proofs of O-minimality. And now, what kind of consequences would you have in mind for, say, in linear algebra?
No, I was curious because cell decomposition gives you the way to quantify elimination to efficient procedures, as you have in linear algebra. And now I wonder what of the simplicity, you know, all this beauty of the O-minimal structure should give you.
Well, you get cell decomposition.
Theorems which help you computationally.
Well, like you do have cell decomposition. And one can go through the proof of cell decomposition and work out the computational complexity of the cells you end up with in terms of the original data. But that presupposes that you have some measure of the original data, and that doesn't make sense in a lot of the O-minimal structures, but it does in some. One particular one investigated by Havansky is where we consider expansions of the real field by functions satisfying certain differential equations. Now, the differential equations come with certain data, the degrees of the polynomials, the degrees of the derivatives in the equation, and so on. And there it has been very deeply studied, the complexity of cell decomposition in terms of the data given by the differential equations. So that's in work of Havansky, Gabrielov, Vorobyov. I could tell you papers where this is done in great detail. Yeah, but your question presupposes certain data about the language to start with, and once you have that, then yes, you can go through the proof of cell decomposition and work out the complexity in terms of that data of the individual cells and number of them. But for these huge, these O-minimal structures with huge languages like R and EXP, that tends not to be a focus. Yeah.